Hi. At this point, I'm just gonna step through the whole process for the research project. I'm gonna try to um, summarize everything so you can be able to produce your plots, graphs, and simulations, MATLAB and EasyNet. So I'm gonna start by doing that with the ground plane dipoles. So I mentioned that for this problem, since the limitations of EasyNet to have a ground plane in different axes, I just made a modification. So the actual problem for the MATLAB and for like the equation derivations is gonna come from this description right here. Uh, so uh, and so let me go back to here. So this is the actual I summarized the the process for calculating your equations for MATLAB. So the problem says that um, the element that's the dipole is aligned the z-axis. So here's a graph of the what we actually looking at. So we got the ground plane in the xz axis, and there's two dipoles are the ones that on the 1 and 2 are the ones that they're like generating an image in the on the other side of the ground plane, which have a different current directions. So the element in these has the characteristic of or radiation pattern element factor of sine theta. This is because it's aligned the z-axis. Okay, so the frequency range is it spans from 200 to 600 megahertz. So we come out with the center frequency of 400 megahertz, and then if the lambda is going to be 0.75 meters. Okay, so I'm referring to this referring to the book Balanis, page 289, and talks about the pattern multiplication for calculating total patterns. So it says that the total pattern of an array of elements is the array factor times the single element at reference point element factor. So the other thing that we're gonna use to derive our equations, we're gonna use these trigonometric identities just to simplify the array factors. So the array factor turns out to be this whole element right here. So in the previous video I showed how we come out with this equation. So this is the equation that you come out after like deriving each of your elements, and then by using these trigonometric identities we come out with this whole equation simplifies into cosine k dx sine theta cosine phi sine k dy sine theta sine phi. The problem gives us the values for dx and dy, and the value for k is equals 2 pi over lambda. So if we replace all those values into this equation, then the E total so after we this is the equation for the array factor, so that E total comes out to be the element factor, which is sine theta, times this equation right here, which is the array factor. Okay, so the problem asks for like a E-plane, E-plane, and H-plane. So so in order to calculate the E-plane, the H-plane, we let the angles to be phi equals to pi divided by 2, or 90 degrees, and then if we replace that into this equation on the E total, then we'll end up with this equation for the E plane, and this is what we're gonna use for MATLAB to plot. I'm gonna demonstrate that on the in a few moments. So for the H plane, we let theta equals pi over 2, or 90 degrees, and then based on these equations, these values, we replace that into the E total equation, and then we'll end up with a value that's like this. Okay, so so we have our equations. This is what we're gonna use to calculate the E plane and H plane patterns. So we come up to MATLAB. We make sure that I'm gonna send you all these files, and make sure you have it under like under a file folder. So in this case, I have MATLAB antenna, and then I'm gonna open for the first case where we have two elements, like we have this case right here. So it's a dual dipole 1 by 1. So I'm gonna open that, and this is the program that I'm gonna be running. So I mentioned before that the equations that I need for MATLAB are these ones for the E plane and the H plane. So those equations are sine theta 0.5, so directivity. So those equations are this one. So we got the E plane and the H plane right here. So this is the H plane and this is the E plane. Okay, and then right after that, I calculate the directivity. So it asks you to calculate the peak directivity of the for this antenna displayed on dB values. So determine the 3, and then after that it asks us to determine the 3 dB E and H plane beamwidth. So this is at this point it calculates the 3 dB value. Okay, and for part B, it asks us to do a study of 0.85. Let me come back here. So for part B, it asks us to do a study. So one thing that I have this thing wrong is, instead of the frequency to be 1000 megahertz or 1 gigahertz as it was before, this is gonna be 400 megahertz. Okay, so make that a change, that assume f is equal to 400 megahertz, which is the center frequency. So we're gonna multiply that by 0.85 and 1.15, and we'll see that the calculation. So that's for part B we multiply that, um, that that we do for so for 0.85, so it's this part right here, and I repeat that for 1.15. Okay, so what I'll do is I'm gonna run this program, um, and then I'm gonna see my plots. Okay, so there's three plots here. The first one is for frequency of 400 megahertz. Um, the other the other one, the second one, oh, the third. Okay, so in this case, third and fifth. So the third one is for the frequency of 340, which is 0.85 times 400 megahertz. So we have 400 megahertz, 340, and this one right here is 460. So so what we can see is that once we start incrementing the frequency, we start seeing side lobes coming up. So that's what we are really what we want to demonstrate actually here, that by increasing the frequency, the separation between the dipoles and the ground plane becomes shorter, and so we start seeing the distance between the ground plane and the dipole becomes higher, longer, so then we start having side lobes here. So that's for part A. That's for like the first. So for this case, we have in easy neck, we had the simulation to be like this. So so this is, as I mentioned before, we are rotating these 90 degrees. So if we actually want to simulate the case that we are having in MATLAB, I just need to rotate these wires around X by 90 degrees, and then I'll have exactly the same case. But in this case, since EasyNet has the ground plane in the X and Y, so it thinks that the wires are being grounded. So that's why I make the changes here. So okay, so in this case, once I have my geometry created and I send you these points, so you could create these. You can enter your wires here, your sources, and then the units is gonna be in wavelengths. The ground plane is gonna be perfect ground plane. Okay, so I'm gonna run this. I'm gonna get the radiation pattern of this. So this is the radiation pattern. So I'm gonna show the 2D plot, and this is gonna be the plot that I'm gonna generate. So the maximum gain is in this case it's in the C, along the C direction, so in the positive C axis, and the gain is equal to, calculated to the directivity is 10.76, because in this case we don't have any losses, so the gain has directivity. So I got 2.76. For the case of calculating okay, so then the other things that I want to get from here is also the beam width, which is 50.2. Okay, and the other stuff that I want to get from here is okay, another stuff that Another plots that I can generate from EasyNet is also like I can calculate the SWR. So for this case, um, okay, so let me back up a little bit and then so if we follow what MATLAB is the problem is asking us, so I'm gonna change these to 340 megahertz, and I'm gonna generate another plot. So as you can see, there is no side lobes in this case. So that's the elevation plot. There is no side lobes. So now I'm gonna increase the frequency to 460. We're gonna see there's an error. That's just warnings. So I'm generate that, and then you can see that right at that point we start seeing side lobes. The side lobes getting bigger. Okay, so just the same demonstration as in MATLAB. EasyNet will give you more than MATLAB gives you. So it actually calculates, takes into account many variables than MATLAB. So this is the closer answer to reality that we can get. Okay, so so that's one thing. So I'm gonna come back and put that back to 400 megahertz. And the other thing that I can generate from this from EasyNet is the SWR. So in order to do that, you gotta enter a start frequency. So I'm just gonna enter 200 megahertz, and the stop frequency is gonna be 600 megahertz. And I'm gonna step. The frequency step is gonna be around 10 megahertz, and I'm gonna run these. And this is my SWR, VSWR. My bandwidth for this, if I take a 3 to 1 VSWR, this is my bandwidth, starting from 400 minus 360, so it's like around 40 megahertz, more or less. The other things that I can get from here is the display. I can get the return loss. In this case, we're looking at that 10 dB, 10 dB point to calculate the bandwidth. The other things that I can get from here is displayed. I can generate a Smith chart, so I can just make sure options and plot. I'm just gonna change the colors to blue colors so I can notice. Okay, so that's the other type of plots that I can generate from EasyNet. But for this case, you'll be enough with this, with generating the radiation pattern. Okay, so that's about it for this case, for the ground plane dipoles. This is the geometry for EasyNet. I'm gonna send you these files, and this is the geometry for the four element dipole. So in this case, it's gonna be eight dipoles if you take into account the ground plane. The equations are like this. So I'm gonna send you this Word file that derives this for this. So that's my my equations, and for the 2x2 array, what we're actually looking at for MATLAB is we're seeing this array of 4 dipoles and 4 dipoles in the other side of the ground plane, and the equation turns out to be the E total to be equals to this, sine theta, cosine k dx, sine theta, cosine phi, sine k dy, sine theta, sine phi, and this is the element that enters once you create um, you have like another two dipoles. So the E plane and the Y plane, if we replace that, it's gonna be this element. You replace that by the element, the values, then this is what we're in the. This is the final value for that. The same thing for the H plane. We replace. We set the theta angle to be pi divided by 2. The angle is 90, and then we end up with a total value of, this is the E total if we replace those values. What I actually want to see on your report is actually these kind of values from MATLAB. So, and those values are gonna be generated when you run MATLAB. So when you run MATLAB, it gives you those values right here. So for the first case, it's gonna be, the frequency is 400. So that's I have the value of 10.4 dBs, which is right here, 10.4. So for the first case, the beam width is 74, and the beam width in the H plane is 50, 15.4, close enough. The directivity is equal to, okay, so that's for the 400 megahertz. For the 340 megahertz, the directivity is equal to 10.03, which is right here, and the beam width is 72 and 56. And for the last case, which is the 460 megahertz, these are the values. So you'll generate these plots right here, this table, and that will be enough. And the same thing for the case of the 2x2 array. So you'll be able to come up with these kind of tables with different values. Okay, so I'm gonna send you this file so you can generate your tables and your values for your report. Okay, so that's about it for the dual dipole. I'm gonna be sending you the MATLAB programs, this file, and EasyNet files. So the only thing you need to do in this case is just generate your plots and write your report. Okay, that's it.